morning. It's the 29th of April 2025. You're welcome back. It's a good morning. This is still on the subject of motors and current and alternating current and power transmission in an effort to be of interest to vintage people, because my channel has a vintage element to it, and also to help people understand what you never get explained to you in any medium. And indeed, I now believe, according to some people, they're not even teaching this in the universities. So motors back EMF, and I've just left the blackout in Spain and the Irish engineers thing there, and the warning about these blackouts and all of this. Now, you'll be up to speed with my 3 videos in 2011. Those videos are very, very important. I can't and don't want to improve on them. And I do find people often ask me, will you tell me that again? Look at the videos are there. That should do. Once is enough to explain it, but sometimes people just won't. Oh, I won't bother looking at them, but you'll tell me, and you find yourself repeating this. If I were to do it for every one of my subscribers, there's nearly 10,000 of them. That's a lot of talking, I'll tell you, and I don't like talking, would you believe? I always point out that in it, who speaks the least in a Clint Eastwood film, and the answer is Clint Eastwood. Anyway, I digress a little bit. There's one feature of electric motors, which are in effect transformers with one magnet moving in relation to the other. Unlike a transformer, they're stationary. But one of the things about motors, they take many different forms. This is the old dynamo. See that? And there's the internal part. And there are brushes. Do you see them sticking out here? Brushes here. And they run again a commutator. Now, the current produced in a dynamo is alternating current. You cannot produce direct current at all in any kind of device. You can't produce it. But you can produce alternating current, and in this case, it's converted to direct current to charge a battery by means of the commutator. Segments, you see them there in that, little segments there. Switch connect, and that draws off the power in a direct way, and actually it's very clean power because it only draws it off at the pole. So that's one type. Now, a starter motor of a car or a tractor is the same, except that the windings in this are designed to feed in power at low amounts over a long period without overheating. And the windings in a starter motor for a car or a tractor, a big heavy yoke, I didn't want to haul it up here, are designed to give high torque for a lesser period. Definitely not an hour. Understand? But the starter of a car has a commutator, and the wear of the commutator is not a big deal. Sometimes they have to be redone. Now, another form of motor, that, by the way, this type of dynamo or motor is what's in all the power tools. Brushes. So a hand drill will have this type. It will have a rotor like this, a commutator, and the whole lot. It'll run on either direct current or battery power, because the brushes convert the current into the right current at the right moment to make it go round. So they're very versatile. And they're in washing machines. Okay? Now just to be one step ahead of the lefties here, they'll be saying my jumper's dirty, I'm handling old stuff lying out in the shed. They want me to wear a brand new jumper and then get it dirtied. No is the answer. Now, in a washing machine, there are various types of motors. This is one. This motor has brushes. You can see them here. There's one, and there's the other. And this motor is identical to the dynamo of the car or the starter motor of your car, except that it's wound to suit the conditions it operates in. And this motor needs no capacitor to start. The problem with this motor is that when you start it up, it will run out so fast, if you don't control the speed, that it'll break. You'll run the bearings. There is no limit to what the speed of this can be. They design them to try and keep it down, and they design them with a load on here and with certain protections built in with modern electronics to make sure they don't run away. Okay, so that's the brush type washing machine motor. If you're using it for something, you have to take this into account. Now, there are control units you can get. All of those brush type motors will run out of control. Now, the only resistance on this, if you were to put it going now, is the bearings here. The bearings and the air will resist them a bit and retard the speed a bit. Now, the problem again with those type motors is you have no control on the speed. It doesn't matter what the frequency of the current coming in is, whether it's a big battery or the mains power or a generator. They can run out of control no matter what the frequency is. The frequency changes, but it doesn't affect these because these have brushes. You understand? So they're very versatile for that reason. Now, and the other thing about it, even for washing machines, the brushes last a long time. Although I have replaced the brushes in my washing machine, you can get them to buy in a kit. If you want to control the speed and you want to have a motor to run on your AC power, you need an AC motor. And there are different types. There are ones of them with brushes called a synchronous motor with wound rotors. But you really don't need all that sophistication. What they do here is a squirrel cage job. They cut segments in the motor, you see them there, and they put aluminium around it. And the aluminium forms a closed magnetic loop and allows these wee pieces to be used as magnets. And these are excited by the rotating field of the stator of the motor. There's a field coil called a stator in here. Okay, beside them. Now, the thing about this is, this runs at a set speed. It's the ratio, there's somehow dirt on that there. It's the ratio of these segments or these poles to the ratio of the frequency, and by changing them you can get different speeds. It'll be rated on it 1750 or 1450 or maybe 22. Usually they're around the 1750 revs per minute. There are bearings in this, and this is the only resistance there is. But these will not run away. These, with the start, they'll come up to speed of the frequency and they'll run at that speed. And they can take a certain load. If you overload them, they start to slip. It's the slippage of the field on these that causes them to be magnetic, and it causes them to be pulled around by the rotating magnetic field inside in the rotor of the motor. Okay, so now whether it's 3-phase, 2-phase or single phase with a capacitor, it's the same principle. They're directly related to the frequency. If it's a single phase motor, the capacitor will have, the motor will have a second coil, a second winding, that will act in between. So when the power is here and the power is here from the mains, it doesn't know which way to go. It'll buzz. It doesn't know which way to go. But when you put your capacitor, your secondary winding, this will pull it when this one isn't. And so the capacitor absorbs some of the power here and releases it here. And that's the most important point that people miss and that students aren't told. The key to a capacitor is that it allows a time delay from it's charged till it's discharged. And that means that when this gets the buzz there, it's round here a little later to pull it on round. And that's designed by the frequency, which is most advantageous, is 50 or 60. 60 in America, 50 here. So when you come along and start messing with your frequency and going back to 47, 53 and all this, you are tricking with this. You're interfering with the whole way these work. And very easily the motor will stop. And then it's buzzing away there and it can't get going again. So the frequency is designed that the capacitor will give the power here and then give it here at the right time. When you start messing around with the frequency, either the capacitor can't act fast enough, by the time it lets go the current for here, the motor's around to here. or it's too fast, too slow, it's too fast, and it gets the injection of power here and it gives it out here, still a problem. So for this reason, you cannot just mess around with the frequency, no matter what the politicians say. And as we know, the grid collapsed in Spain yesterday. Now, another part I want to deal with here in the time available, that's 10 minutes. Another part I want to deal with. When you take any motor, they're a generator in reverse. Technically, if you put the current on here, either direct or alternating, put the current in here, this will spin round. If you spin this round, it will give out a current. This dynamo can have current fed into the brushes, fed out from the brush, fed out through the wires here, out to light the lights on the car and work the wiper and charge the battery. But if this is spun, it will do the opposite. And I showed you an example of a verticut rapeseed oil cutter which tried to use a dynamo like this as its motor. But they're wound to be very weak on actually acting as a motor and very strong on actually acting as a generator. But they work both ways. When any of these are running, no matter what they are, this one, or this one, the power is absorbed to get them started. Okay? If you have this one, you'll see a capacitor on it. And a capacitor might be the size of this bottle for a very small one. Or it might be the size of the inside of a toilet roll. I have none here, I think. Might be an example. Wait till I see. It might be this size or a little longer. Generally, that size of a capacitor is small, and it will be for a capacitor run motor only, because it only needs to get it up to speed. It doesn't need to stay going all the time. If it's a capacitor run motor, and by the way, these type of ones with the capacitor start are quite efficient. They rarely give any trouble. They nearly go straight away. If it's a capacitor run motor, your capacitor could be the size of that book, and I have no other books here. We get the whole lot of them. It could be this size, and it is on my drill press. So it could be this size here. Big thick one. Why? Because it has to keep going all the time. Whereas the other one only has to be this size for the start one. So the capacitor run one will need a bigger capacitor. Not only that, the capacitor run one, the capacitor isn't as good to get started. They can give you trouble starting and there'll be buzz in there, whereas the other one does. So what they do is, for most applications, to stay away from the capacitor run motors because of that, this extra size and everything. And they go to the capacitor start only. Okay, now what I wanted to get to now is that when you feed the power into this here, it starts spinning. And as it starts spinning, it also at the same time generates power. You cannot spin this by any means without generating power. It's impossible. So you take this here and you put a battery to it and it spins around. It's generating power, and that's known as back EMF, back electromagnetic force. So as the power is going into a motor, it's coming out the same way. And if you let the motor run for a while and no load, the only load will be the bearings and the air resistance. Get my point? So if you take the motor and you apply a load, you reduce the back EMF. It generates less back EMF. When the motor is running free, it won't overheat because it's only using maybe 5% of the power it needs. There's 100% going in, there's 95% coming out. Or if you increase the load a bit, there's 100% going in and there's 80% coming back out. So the battery is actually driving it and it's being charged at the same time, because you cannot run a motor without it creating back EMF. So when you put the battery of the car to this, it spins around, and when it's spinning, it's generating current. The dynamo doesn't know who's spinning it. All it knows is if it's going round, it's creating back EMF and power. Understand that? So if you're driving this with the mains, it'll run mad. It could bust on you. But it's using very little mains, because for every unit it takes in, it's putting in 97% of a unit. Get me point? Back EMF. And that's why a motor can run without a load, without burning out. Don't forget, when you put the mains onto the coils of any coil, it'll heat up. You have to have a very long wire in the coil, in the transformer, to avoid it heating up. But you can get away with shorter ones in these machines, because they are only using a fraction of the power that goes into them, because the rest of it's coming back out. And if you take 100 minus 90, that's 10. Only 10 is being used. So as you increase the load, the amount of back EMF is less. So you have 100 going in, and as you increase the load, you might have only 20 coming out. And if that happens, the motor will heat up. And if you block it completely, it will burn out, because there's no back EMF to compensate for the electricity going in. Have I explained that? That's a very important concept. So if you take a big generator down in Ardnacrusha in Ireland, generating for the ESB, yes, it's generating electricity and pushing it out. It's generating, it's pushing it out. The only back EMF there would be then, if that's driving motors in a factory up the road, the motors will be flying around, and they're creating back EMF, and that relieves the load of the generator at the power station. So there's actually power flowing out on the wires and flowing back in. Isn't that unbelievable? And if you cut the power station, suddenly the rotors will continue to spin, and then still continue to send back EMF back up the wires. Back electromagnetic force. If you don't believe me, you can Google it. They call it back EMF as far as I can remember. And that's a big feature of all motors. Now this applies whether it's single phase or three phase or whatever. But the three phase is the most efficient, of course. So I think I've explained that about your capacitors and all of that. Some man asked me about the power factor situation. Now that's a slightly different thing. When a motor receives its phase, the voltage rises prior, usually, to the current. It gets the voltage seems to travel slightly faster than the current. So you don't get the full value. So as the voltage is rising, you're not, and the current is following, you don't start getting value until both are into play. So as this goes on round, then you still have play. Now the voltage goes, you're out of play. So just to show to you again, if the voltage and the current are the same, you have a wave like this. Happy days, right? Happy days. If the voltage comes in a bit sooner, it's rising, but you have no current to do anything. So it's not until the current comes up that you begin to get useful energy. It goes on round here, you still have the useful energy, but as you go down here now, you see the voltage collapses, and you're up here with this, and this is no good, because the current without voltage multiplied by amps is watts. So this is the voltage, and this is the amps. Now usually they're quite close together, but they can part a wee bit, and it's partly similar to the delay in the capacitor. Certain electrical functions have a tiny delay in them, and without that delay, our world wouldn't be the way it is. That everything seems to be built so that it suits mankind. Isn't that a funny one? So if you throw a switch here, and there's a big light over there, the voltage rises first, and then the amperage rises slightly, only slightly after it. But the result is you don't get the full value. Just look again, this is full value, and this here is less. You see, so you only come in here, see me wobbling my finger, and you go on around, and then this goes out, see me wobbling this way. Now you have nothing here, so you only have this. That's extreme. In reality, you're talking about 2%, maybe 3%, and that's the power factor. When they're making motors, they will give a power factor, and 1 is the perfect. 1 is when the two are together, and then as they come apart a bit, the power factor goes down. Does that explain it? That gives you a kind of an idea. But it's not connected with capacitors, except that the capacitor has a tiny delay in it absorbing, in its charging up and discharging. That's a bit complicated. I hope that's a bit of a help, and I hope it's interesting. If the video is entertaining, even though you don't get it all. Sure, it's a bit of fun anyway. Look at this motor out of a washing machine. That is a perfect motor, and they're being dumped. I hope the Chinese are recycling these and not dumping them. It is a mortal sin to recycle this. There's a perfect bit of kit. Now they're controlled by controls inside with software to give them the various speeds to make them go front ways and back ways and everything else. But some washing machines have this type. Some washing machines have the synchronous type single phase motor. None of them have 3-phase because 3-phase is not normal in domestic situations. They could possibly have them in where you have big washing units and that. I'm not too sure. Okay, is that enough? We'll let you go and I'll get on with my work today. And that is on how many minutes there, folks? 21 minutes, that's enough. Anyway, to go back to the whole thing, the thing in Spain, you mightn't be telling this to any government, and this is the sad part. Any type of professional or any type of proper testing or analysis or assessment is anathema to them. They won't do it. And they won't do it because their voters wouldn't tolerate it. It's our own people that are causing our misery, in my honest opinion. Good luck, comment underneath and have a bit of fun with these videos. There'll be some lads saying, you couldn't wash your jumper, and leave it to the professionals. So we'll see you back soon. Bye.